Hello, welcome. We're going to be looking at Physics 220, lab number 1. We appreciate your patience in trying to adjust to the online curriculum for this term. Hopefully these videos are still instructive and help you understand the concepts a little bit better. Today we're going to be looking at Coulomb's law, an important force in electrostatics. And in order to investigate that force, we're going to be, we have two charge holding balls, as well as this torsion balance by which we can measure the force between the balls. Okay, so in order to charge up these balls, we have a couple different methods that we can do. The first thing that we're going to want to do is ground them to make sure that they're both electrically neutral at the beginning. Now you can get some charge by, like rubbing some of these different materials. One way that I would recommend is just using this one fly stick, because we can charge more the balls a little bit quicker. So we just press it down. So as we hold this fun fly stick to the edge of one of the balls, we're inserting charges, electric electrons into these balls, and they're transferring. If we're inserting electrons here, they're going to want to redistribute. And so we're basically just assigning both balls a negative charge. And then if we release, we can see that they're repelling, okay? And as we move this ball in, we see that it pushes this ball out further. If we put this ball further away, it's going to naturally want to re-equilibrate to its natural position. And so in order to measure this force here, what we have is a torsion balance. Now, the torsion balance, it works as we turn this spindle. We're applying a torque to the wire, which is actually causing this whole thing to move. So I'm going to turn it this way, and we see the whole thing shift out. If I turn it the other way, we see it shift in. So we're just torquing this ball in and out. And for any angle on this balance, there's a conversion factor. And so for one angle, it's 2.36 times 10 to the negative 5th newtons that is being applied in terms of torque on the ball. And so based on what we're going to do is we're going to find the angle that allows this to be where it originally was at its 0 mark, and then when this is at our desired separation length, and then based on that angle, we know the force between the two balls, because we have the conversion factor. It's on your student sheet as well. And so we're going to do that for a couple different trials, and we're going to measure how that force changes as we move the ball back, as well as when we take half the charge off of this ball. And so we do that by taking one of these balls. We want to hold them from the end of the rod so that we're not allowing charge to flow into our bodies. But we have just this grounding plate. We want to make sure it's grounded. And we just touch this grounded ball to the other ball. Half of the charge is going to now move on to this ball. So we've decreased the charge on this by half. And now we can see this has moved inward, because there's not as much repulsion force, because there's not as much charge on the balls that are separated. All right, so let's go ahead and begin the data collection here. So the first thing that we're going to want to note is that this is zeroed. And so on the spindle down there, it's on the 0 mark. And this is all grounded, so there's no charges on the sphere. So when it's just naturally sitting here, it's kind of perpendicular to the table. And one thing that's really important to notice is there's this line here, and there's a matching line on the spindle, and these are lined up. And then also, if we look from above, there is a hole. Maybe it's there. It is, yeah. So there's a hole here, and there's another hole that's in the protractor type thing that turns. And so we're going to know when we're zeroed by if these holes line up, and you can see through them. And so what we're going to go ahead and do is we're going to go ahead and charge up the spheres and then adjust them so they're 15 centimeters apart. Putting charge on the spheres will make them repel each other, and so this will shift out, and then we can turn the spindle until we go back to the 0 point, which we can tell by when we can look through the hole and when these lines line up. And then based on the angle that we need to turn the spindle to apply a torsion to move this back to equilibrium, we can find the force between the spheres. And so another thing that we want to note is that if we want to measure 15 centimeters separation between the center of the spheres, that if we look directly down on this, that we're at 5 centimeters. So if I'm just looking directly down from the center of the sphere to the meter stick below, the center's at 5 centimeters when it's zeroed, parallel to the table. And so we want to go 5 centimeters, 15 out to 20 centimeters is where we want the center of this to be. Now, one thing, I'm going to put this off here, is that if we want the center to be at 20, if we want this center to come down and be at 20, we need to have the end here at 18. Yep, that looks about right. Maybe 18.2. So if we move the end to 18.2, the center's at 20, this one is at 5, and the centers are separated by 15 centimeters. So I'm going to use the fun fly stick just because it'll charge them up faster and get more charge here. So I'm just holding this against the 1. This is again causing electrons to move in here, and they're going to redistribute themselves. Okay, and then if I remove it, you can see that they're repelling. Okay, before this was just straight perpendicular. And so I'm going to go ahead and move this back to our value we decided earlier, 18.2. And then when this goes back to equilibrium, they'll be separated by exactly 15 centimeters. So I'm going to go ahead and move it out. I just moved it out 30 degrees initially. And that brought it a lot closer, but we're not quite there. So I'm going to try moving it over to 40 degrees. And I'm just trying to get it pretty close. And then I'll do some more minor adjustments. Okay, we're a little bit closer now. And I'm looking through the center. And I think we got pretty lucky. Sometimes we have to adjust it back and forth for a while, but that looks 0 to me. So let's go ahead and record that angle. The thing to note is that there's 30 there. These black lines are 10. So this would be 30, 40, 50. So we're at 40.7-ish. But you can make your own measurement there. And again, this is 15 centimeters separation. Now we want to go ahead and make this 25 centimeter separation. So I'm going to go ahead and move this back till the edge is at 28.2. So we moved it back exactly 10. You'll notice that it went in because now the Coulomb force is less than it was before. And so the torsion force is stronger and it's causing it to move in. So I'm going to decrease the torsion force until we're back to the equilibrium. So I'm just moving back on the spindle, decreasing the torsion, and we see it moving back to where it is when zeroed. So it moves kind of slowly, so I want to wait to see how it adjusts. I think I moved it too far. And we're going back out. So I'll go down a little bit. This is usually what it entails, lots of back and forth, which does take a little bit of time. But this torsion balance is very precise. It enables us to measure these really small Coulomb forces very accurately, which is why we're using it. And this is zeroed right now, so this is for a separation of 25 centimeters. And there's our angle there. So now what we're going to go ahead and do is ground the charges, ground the two spheres. So they're now electrically neutral. And we're going to follow the same procedure at the 15 centimeter mark. We're going to charge them up, separate them by 15 centimeters. And this time we're going to take half of the charge from one of the spheres off of it and see how the force responds. The reason why we're recharging them is because there is some charge leakage just to the air. And so we want to, in order to see how these changes affect the electrostatic force, we want to try to keep the charge the same throughout all the trials. So that's why we split it into two parts. Okay, this is probably good there. All right, so I'm gonna move this back out to 18.2. And again, I'm gonna go ahead and put this out. I went ahead and just put it back to the same value. Now, one thing you'll notice is that this is actually a higher force than we originally did, and that's because I just held the fun fly stick there longer, so we have more charge on the two spheres. So it doesn't actually matter how much we charge them up, but we just want it to be consistent across these two different sections. Okay, that looks good to me. So we're almost at 90 degrees here. So this is definitely a bigger force than we had before. Now let's go ahead and take this. I'm gripping it by the end of the fiberglass rod so that no charge leaks to me. I'm just going to touch it here. So I've removed half of the charge from the sphere, and we see that they went in. So the force decreased, which is what we would expect. Now I'm going to go ahead and adjust back to equilibrium so that we can measure the force here. Okay, that looks pretty good to me. So we're a little bit less than 50. And so that's all the data collection here. One thing to note is that this formula to find the angle, you take the angle, multiply it by this conversion factor right here, and then from there we can get the force. And so we're going to do that for all the angle measurements that we took. 1, 2, 3, 4. And then from there it's just a simple matter of some math, doing some of these ratios before and after. The predicted, one thing for most of these labs to know is that when we refer to predicted, where we want to plug in values to this equation here and see what the mathematical model would predict, and then the measured is like what we actually got. And so these two values should be close. They should line up. In a perfect world, they would be the same. There's probably some measurement error and some charge leakage, so they may be a little bit off, but they should be on the same order of magnitude there. And that is all that you have to do for this lab. Hope that you enjoyed it. If you have questions, don't be afraid to reach out to a TA. Thanks for watching.